All right, two variable statistics, part one. So this is all things regression, all things correlation. Not to be confused with the two variable statistics option in your calculator. This is regression. There's some relationship between these two quantitative variables. Two variable statistics is a lot. We're going to cover it over the course of two videos. Through that, we're going to talk about scatter plots, correlation, coefficient of determination, the regression equation, what a residual is, how to tell if a linear model is appropriate, and we're going to talk about influential points, outliers, and transformations. This slide gives you a little bit more detail on those ideas. Scatter plots, how to make a good graph, how to estimate correlation, etc. Using and making the regression equation, and then some more ideas that we're going to get through between this video and the next. So let's just get right into it. Scatter plots, good graphs. That's the first thing we need to worry about. When we make a graph, we should always label our axes, right? So that's the first thing. Make sure that your axes are labeled. It should be very easy for me to read your graph. The way we describe a scatter plot is using another acronym. So remember, for one variable statistics, there's COVs. For this, there's DOFs. So we're looking for direction, outliers, form, and strength. And we might even say, instead of outliers, we might say unusual. Let me do it this way. Let's do it that way. Might say unusual features instead of just outliers. Remember, for form, we can say linear curve, or if we actually can tell that it's an exponential or a quadratic or something, you can say that. But again, make sure that you're using wiggle words. Give yourself like approximately, about, something like that. Don't overly commit to an answer, because if you've overly committed, then it could be wrong. And stats is all about estimation. More about scatter plots. Correlation. Correlation measures the strength of the linear relationship between the x and the y variables. The stronger the relationship, the more tightly packed the scatter plot is in a line. The closer the correlation will be to either 1 or -1. Remember, +1 is if it looks like that. -1 would be looking like that. To calculate this from a data set, you'll just enter all the data and do a lin-reg in your calculator. And that'll also give you the coefficient of determination when you run that. So that segues us nicely into what is the coefficient of determination. Coefficient of determination is the proportion of variability in y that can be explained by x. Now I realize I was just trying to come up with a definition in my head, and I had it written right here the whole time, right? So it's the proportion of variation in y that can be explained by x. It's going to always be reported as a decimal. We usually talk about it as a percent, so you'll probably want to convert that. On computer output, it's going to be called r-square. So we'll see that once we get there. The regression equation itself is y hat equals b sub 0 plus b sub 1x. This is our y-intercept. And then b sub 1 is our slope. So they'll be given to you when you run lin-reg in your calculator. They'll also be present in computer output. So I've written how you find it, but I'll point it out in the next couple slides because we're going to do it a couple times. But the coef column, or coefficient, sometimes it's written out all the way. That's where you're going to get your slope and your y-intercept. The constant one is your y-intercept. I'll show you that on the next couple slides of problems that we're going to actually do, I think. Nope, but they're coming. There are two formulas on the formula sheet that are actually going to help you with that. One of them, I can remember off the top of my head, is B1 equals R, standard deviation of Y, standard deviation of X. The other one, I believe, is B sub 0 equals Y bar minus B sub 1 X bar. I believe that's it, but when we actually have our formula sheets, we can verify that that is the correct formula. I'm pretty sure it is, though. The way we interpret the slope is the predicted change in y when x increases by 1. We have to say predicted. We don't know that y is going to increase. Y could decrease, but is our prediction that it will increase by the slope. The y-intercept is the predicted value of y when x is 0. Again, make sure you're using words like predicted or expected. We can actually use the regression equation to make estimates for particular values of x. All you got to do is plug in the x value. Make sure that you're careful of interpolation versus extrapolation, though. Extrapolation is when if our data set goes from, say, 0 to 6, right? Those are the x values that we know about. If I use x equals 9 in my regression equation, that's outside of the interval of known x values. So that's a little sketchy. You might want to avoid that. And if you do use that, then you need to be cautious with the result. And a lot of questions will ask like, oh, should you use this? And the answer would be no, because outside of the interval where we are comfortable, things could go haywire. All right, let's do some actual problems. Delivery service places packages into large containers before flying them across the country. These filled containers vary greatly in their weight. Suppose the delivery service's airplanes always transport 2 such containers, and the 2 containers are chosen so their combined weight is close to but does not exceed a specific limit. A random sample of flights with these containers is taken, and the weight of each of the containers on each selected flight is recorded. The weight of the 2 containers on the same flight will have a correlation of 0, negative, etc. Okay, this is a really tough problem, honestly. I kind of wish I hadn't started with this, but that's fine. So we have the 2 shipping containers. We'll call them shipping container A and shipping container B. There's a weight limit. So let's say the weight limit is, I don't know, 750. We're just going to do this by maximums because it'll be easier to understand. So if A was 250, B could be up to 500. If A was 400, B could be 350. If A was 600, B could be 150. Up to 150, right? So I think what we can see here is as one goes up, the other goes down. Now, I don't have to have this perfect correlation that I'm illustrating in the table that I'm showing. But as one goes up, the other has to go down, which means that we're going to have a negative correlation. I think that's kind of hard to come up with on your own, but there it is. Great. The computer output below shows the result of a linear regression analysis for predicting the concentration of zinc in parts per million from the concentration of lead in parts per million found in fish from a certain river. So they're predicting zinc by measuring lead. Which of the following statements is a correct interpretation of the value 19.0 in the output? Okay, so let's find 19.0 in the output. It's in the coefficient column I was telling you about. So that's either the slope or the y-intercept. Well, it's going with a variable. It's going with the variable lead. That means 19 is the slope. Which means 16.3, not that it's asking about that, is the y-intercept. Okay, so we know this is slope, so we should be looking for something about the predicted amount of zinc increases by 19.3 for every increase of 1 for lead. So we need something like that. Predicted increase in y for every increase by x in x by 1. So let's read the first one. It says, on average, there is a predicted increase of 19.0 parts per million in concentration of lead for every increase of 1 in zinc. So this one is x and this is y. So we have that backwards, so that's not our answer. On average, there is a predicted increase of 19 in the concentration of zinc, that's my y, for every increase of 1 part per million in concentration of lead. That's looking good. Let's read through the other answers just to make sure though, but I'm pretty sure it's B. C says the predicted concentration of zinc is 19 in fish with no concentration of lead. That's them trying to interpret the y-intercept. So they're trying to catch you off guard and see if you don't know which number that is. And then D is just getting the variables backwards. Approximately 19% of the variability in zinc concentration is predicted by its linear relationship with lead concentration. That's them trying to interpret R squared. So that one's not right either. So B is the correct answer. Perfect. All right, a newspaper in Germany reported that the more semesters needed to complete an academic program at the university, the greater the starting salary in the first year of a job. The report was based on a study that used a random sample of 24 people who had recently completed an academic program. Information was collected on the number of semesters each person in the sample needed to complete the program and the starting salary in thousands of euros for the first year of a job. The data are shown in the scatter plot below. The table below shows computer output from a linear regression analysis on the data. Identify the slope and interpret the slope in context. Okay, so same skill as the last one, right? We need to find the slope, so it's in this column. The one that has a variable, that's my slope. So the slope, I'll say b sub 1 equals 1.1594. and I'll interpret it over here in this big white space that I left myself. For every additional semester, because that's my X, semester in an academic program, it is expected, or it is predicted, something that gives me that flexibility. It is expected that salary will increase by, now remember, this is being measured in thousands of euros. So I'm going to say, I'm going to move my decimal over by 1,159.40 euros. No, I don't think euros is capitalized. It's not. Oh well, not a big deal. Okay, next one. Based on the people in the sample, describe the association between starting salary and number of semesters for the business major. So we've got to be careful. They've changed the dots, right? So an independent researcher organized this for us. It broke it down by major. So we're not looking at chemistry. We're not looking at business. No, sorry, we're not looking at physics. We very specifically are looking at business, right? So when I'm describing a scatter plot, remember I'm supposed to use DOFs or DUFs, whichever one you prefer, which is direction, unusual features, form, and strength. So I'm going to talk this out loud. Direction, it's negative, right? It's going downward. There are no unusual features that I can tell. It's definitely looking linear, and it's pretty strong association. So the association between starting salary and number of semesters you're just going to pretend that that looks like something legible, of semesters for business majors is strong, negative, and linear with no unusual features. All right, there you are. All right, I got a couple more. The manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. As soon as the selected customer entered the end of a checkout line, data were collected on the number of customers in line who were in front of the selected customer and the time in seconds until the selected customer was finished with the checkout. He picked a person and then saw how long it took them to check out. He also counted how many people were already in line when they got there. That was a lot to unpack. The data are shown in the following scatter plot along with corresponding least squares regression line and computer output. Identify and interpret in context the estimate of the intercept. So we're doing the intercept this time for the least squares regression line. So that's again going to be in the coef column. Remember, the intercept is the constant, so it's this one. So y-intercept is 72.95. And remember, that's the predicted value of y when x is 0. So for us, the predicted checkout time is 72.95 seconds when there are no customers already in line. Great. Last thing, identify and interpret in context the coefficient of determination. So the coefficient of determination, r squared, they even told you r squared. They kind of gave you a hint what to look for. So r squared is equal to 0.7333. So remember, r squared is a decimal, not necessarily a percent. I'm actually not sure if they'd take both, but I always do it as a decimal. So now I need to interpret that. So 73.33% of the variation in checkout time can be explained by the number of customers in line. All right, and that is it for the first half of two variable statistics. Watch out for the next one.